In this series of PowerPoints, I'm going to go through the PowerPoints on the Kinetics unit, and it's broken up into the instantaneous rate concept, the differential rate law concept, the integrated rate law concept, and then mechanisms and catalysts. So this first screencast is on the general idea of kinetics, and then we'll go through instantaneous rates. So what is kinetics? It's the study of the speeds or the rates of chemical reactions and how we can speed them up and slow them down and control their rates, and how the rate of one component of the reaction affects the rate of the other components of the reaction. So the two things that we need to understand is how to determine the rates at which a reaction occurs, and how factors within the reaction can control these rates. So one key concept when we're talking about kinetics is to understand that reactions involve breaking and forming bonds, and the speed of reaction depends on the nature of the reactants. It's all about the frequency of the collisions between the molecules. So the more frequent the collisions, the faster the reaction will happen. So how can we get more collisions? There's a couple of things that you can have. So the physical state of the reactants, if the reactants are in the same state, they're more likely to react. So reactants in different states are limited to their area of contact or their surface area. The concentration of the reactants. If you have a higher concentration of reactants, they're more likely to interact. So one reactant, high concentration of one reactant makes reactions easier because you're more likely to have collisions. The temperature at which the reaction occurs, because if you're at a higher temperature, the reactants are going to be moving faster, which means they're more likely to have collisions. So gases at a high temperature have a higher kinetic energy, therefore they collide more frequently, therefore you're more likely to have a collision that is going to cause the breaking of bonds, and therefore the reaction is more likely to happen. The presence of a catalyst. Now, what a catalyst does is reduces the activation energy, and that helps the collision be more effective, meaning the causing of the breaking of the bond. It allows for accurate orientation within the collision. So catalysts will help you speed up reactions by lowering the activation energy. So if we have any of these factors or multiples of these factors, then we can make a reaction go faster. It's like bumper cars. If you just have two bumper cars in the bumper car arena, well, they're just going to be chasing each other. But more bumper cars, then you have more collisions, and more collisions makes things more interesting. More bumper cars, more collisions. Now, what makes good collisions? Well, we don't want to just like bump each other. We want to T-bone each other. Now we're talking bumper cars, not cars on the road. So those are effective collisions. We want more collisions with the correct orientation. So that if you have more collisions with the correct orientation, then that's going to cause the reaction to happen faster. What does that mean? We're going to be breaking bonds. And then if we break the bonds, then we can make the bonds, and that's the whole point of a reaction, is to break bonds, which then we make new bonds, and that's what happens in the products. So, collision theory. Collision theory is we have to overcome Coulombic attractions between bonded atoms and their shared electrons. Collisions must have enough energy, meaning they must be forceful enough, with the correct orientation. That is what's considered an effective collision. So two atoms or two molecules must collide with each other, and they must collide with each other in the correct orientation and with enough force. If they do, then that's considered an effective collision, and that will cause the bond to be broken. If there isn't enough force, well, they'll just bounce off of each other. If it's not the correct orientation, well, then they'll just bounce off of each other. But if they have both of those things, then the bond can be broken and the reaction can happen. So only a small percentage of collisions between reactants have enough force and the correct orientation to be effective. So reactants must have a lot of collisions in order for a reaction to occur, because only a few of those collisions are actually going to be effective. By increasing the concentration of reactants, then you are increasing the likelihood of effective collisions. By making a larger surface area, by increasing the temperature, you're causing more collisions and therefore more effective collisions, which increases the rate of a reaction. So here's an example of collision theory with the incorrect orientation and then with the correct orientation. So here we have two molecules. So before the collision, these two molecules are trying to run into each other. And they are, one's coming this way and one's coming this way. And they're going to run into each other. And the green and the green run into each other. And they have an effective collision. And the two chlorines form a bond here. And the bond is broken between the chlorine and from this molecule, and the chlorine escapes, and we get a reaction. Now, what happened here? In the second example, this one's coming this way, and this molecule is coming this way. Well, we don't have an effective collision. Why is this an ineffective collision? It has to do with the orientation. The chlorine doesn't run into the other chlorine. It runs into the oxygen, and so that's not going to work because we're not going to make a Cl2. We didn't have an effective collision. So it's all about orientation and effective and having enough force. So now that we have a little background on what makes reactions happen, so now how do we measure the speed of a reaction? Well, the speed of a reaction is called the reaction rate, and it's the change in concentration over the change in time. So we can calculate that by calculating the change in the concentration. So delta is change in the concentration divided by the change in time. And if we have data on concentration over a period of time, we can just calculate that. Remember, delta just means it's a state function, and it's the difference between the final and the initial. So we just look at the final concentration. So we'll just say the concentration of reactant A or product A, it doesn't matter. And we're going to subtract the initial concentration or at a specific time. So we'll say initial and divide that by the time, the final time, minus the initial time or the time that we're referring to. And we subtract that. So you just subtract the initial concentration from the final concentration, the initial time from the final time, and that's going to give you your rate. Now, when you are talking about products, the rates are going to be positive because your concentration is going to go up. When you're talking about reactants, your rate is going to end up being negative because your concentration is going to go down. And so mathematically, this part will end up being negative. So don't get worried about end up having negatives because you're talking about disappearance. And you'll see that sometimes the sign is implied in the words. So because products are appearing means positive, and disappearing means negative. Reactants are disappearing, so that means negative. All right, so let's look at a reaction. So we have this reaction, and the reaction is in a container, and let's just assume that the volume of this container is 1 liter. And so the container starts with 1 mole of A and no moles of B. And then we can look in the container, and so after 20 seconds, so the time that has elapsed from here to here is 20 seconds, and we've used some A and we've made some B. And the amount of A used is equal to the amount of B made. So really we can just look at the reaction, and the reaction ends up being A yields B because the stoichiometry. And then after another 20 seconds, because now we're at 40 seconds, we've used some more A and we've made some more B. Now you can actually tell that after 20 seconds, the reaction is slowed down a little bit. Why is that? Well, there's not as much A in here anymore. So after the first 20 seconds, we made 46.46 moles of B. But after the second 20 seconds, we only made an additional, a little bit less moles of B. And that's because our concentration of our reactants are decreasing. So we're having fewer and fewer collisions, allowing us to make B. Okay, so let's do some calculating and see what is the average rate of the appearance of B in the first 20 seconds of reacting. Okay, so we got to remember that the rate is the change in concentration over the change in time. Okay, so what's our change in concentration of B? Okay, so from 0 to 20, so it's final minus initial. So the change in concentration of B over the change in time. So what was the final concentration of B? Well, it's 0.46 moles in 1 liter, so that would be 0.46 molar minus, what was it initially? Well, it was 0 molar. And what is the change in time? Well, it was 20 seconds minus 0 seconds. So that gives us 0.46 molar divided by 20 seconds. And so all we do is 0.46 divided by 20. And that gives us 0.023 molar per second. And that is our rate over the first part of the reaction. All right, what about the second one? It says, what is the average rate of disappearance of A from 20 to 40 seconds? So what about A from 20 to 40 seconds? So at 40 seconds, A is 0.3 molar. At 20 seconds, it's 0.54 molar. And our time was 40 seconds minus 20 seconds. And so what does that give us? That gives us 0.24 molar per 20 seconds, negative 0.24. Which would give us negative 0.012 molar per second. Last one says, calculate the average rate of the disappearance of B over the time interval 0 to 40 seconds. So 0 to 40 seconds, what's the average rate of B? So B is 0.7 molar at 40, and B started at 0 molar. 40 seconds to 0 seconds. So that would be 0.7 molar over 40 seconds. So 0.7 divided by 40, and that gives us 0.0175 molar per second. So it's really just change in concentration over change in time. Oops. And there's your answers worked out. In case you wanted to see it, this is straight from the PowerPoint. Okay, graphical representations of rate. So a lot of times on the AP exam, you'll see a graph that shows you this curve of what happens to a reactant over the course of a reaction. And you can see that over the course of a reaction, well, number one, this is a reactant, and the reason I know it's a reactant is because we start with some of it, because its initial concentration is high, and the concentration is going to decrease. So you can see that it's a curve, and it is going down. Now, why is it a curve? Well, as we are decreasing, as we are going through the reaction, the concentration is decreasing because we are using the reactant. And so the concentration is going to go down, 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 down. Now, why is it a curve? Well, the rate is the slope of the line tangent to the curve. Change in y over change in x. And so this graph demonstrates what happens to the rate as the reaction proceeds. When we first start, the reaction is going to go fairly fast. Why? Because our concentration is pretty high. But as the reaction proceeds, it's going to start slowing down because the concentration of the reactants are going to decrease and decrease and decrease. So the reaction is going to start slowing down. We have fewer reactants available, and when we have fewer reactants available, the reaction is going to start slowing down. Why is it going to start slowing down? We'll have fewer collisions with the correct orientation, so we won't get as many products being formed. So this curve will help you see that as we go through this unit. A lot of times they will ask you to look at this curve and read the curve. Just know that it's just demonstrating that the rate of the reaction is going to slow down as time progresses. So let's get into instantaneous rates. And this is just like if you know the rate of one thing, what's the rate of the other things? It's really just stoichiometry. So molar ratios dictate the relationships between the rate of the appearance of the products and the rate of the disappearance of the reactants. So if we have, in general, a reaction, so this is classic from the textbooks. If we have A plus B, little a and little b being its stoichiometric ratios, so reactant A and reactant B, and they are going to produce product C and product D. So what can we say about their rates? So what's their mathematical relationship? 1 over little a is the rate of A, and that's equal to 1 over little b, the rate of B, and that's equal to 1 over C, the rate of C, and 1 over little d is the rate of D. So that's their relationship. Now these are reactants, so they're really disappearing, so they get negatives. So really this is just their stoichiometric relationships. So if you know the rate of A, then you can find the rate of B just by looking at their stoichiometric relationships. Now, I'm going to be honest, this confuses me. So I just like to compare them and look at their stoichiometric relationships and go, well, which one's faster? Well, how much faster? And why? And let's go from there. So let's look at this reaction. So for the reaction, A yields B. What can we say about them? Well, for every one A, don't we get one B? So what can we say about their rates? Well, their rates are going to be the same. Why? Because they're in a 1-to-1 ratio. So the rate of A is going to equal the rate of B. So if I know the rate of A, I know the rate of B, and vice versa. If I know the rate of B, I know the rate of A. What about the next reaction? C yields 2D. So which one's faster? C or D? For every one C, I get 2D. So aren't I making D twice as fast as I'm using C? So what can I say about the disappearance of C? Well, isn't it half the rate of the appearance of D? Because they're in a 1-to-2 ratio. Or you could say D's rate is twice as fast as C. So basically, the faster one, D is the faster one. Why? Because its coefficient is the bigger one. So I like to do it that way. I like to look at the two and go, well, which one's faster? The one with the bigger coefficient. How much faster? Whatever its coefficient is, it's that much faster. Now, if they're in a 1-to-2 or a 1-to-3 or a 1-to-4 ratio, that's easy. When they're not in a 1 to whatever ratio, then you got to do a little bit of thinking. We'll get to one of those in a minute. All right, so here's some practice. Q yields 4x. Which component is faster? Well, x is faster. How much faster? It's 4 times faster. So if x is 4 times faster, what can we say about Q? Well, then Q is 1/4 the ratio of x. Q would be 1/4 whatever the rate of x is. Okay? So it's just about their stoichiometric ratios. So there's your answers. All right, let's practice. This is where they get a little bit confusing because none of them are 1. So how is the rate at which ozone disappears related to the rate at which oxygen appears? So for every 2 ozone, we get 3 oxygen. So just based on these stoichiometric ratios, 2 and 3, which one's faster? The oxygen's faster. How much faster? If we know ozone, how much faster is oxygen? Oxygen is 3/2 faster. Okay? So if oxygen is 3/2 faster, what can we say about ozone? Isn't ozone 2/3 oxygen? Because it's slower. So using that idea, now let's put an actual number in there. If the rate of oxygen is known, so this is the rate of oxygen, 6 times 10 to the -5. They're giving us the rate of oxygen. What's the rate of ozone? All right, so what do we know? Oxygen's faster. How much faster? It's 3/2 faster. Okay, so if oxygen's 3/2 faster, then what's the rate of the disappearing of ozone? Okay, so we know oxygen, so what's ozone? So ozone's going to be slower. How much slower? It's going to be 2/3 what oxygen is. So what is ozone going to be? Here it is. There's what oxygen is. Ozone is 2/3 what oxygen is. So ozone is 4 times 10 to the negative 3. Now here's what you can do to make it a little bit easier. Do you see that I just used stoichiometry here? Because this is what ozone is. And for every 3 moles of ozone, I'm getting 2 moles of oxygen. And therefore, this is the rate of oxygen. Okay? It's 2/3 what oxygen is. So this is the rate of ozone. So you can really just use stoichiometry to get there. So this is ozone. This is the rate of ozone. And for every 3 moles of ozone, 2 moles of oxygen. Ozone cancels out, and that's going to leave me 4 times 10 to the negative 5 molar per second of oxygen. So it's really just a stoichiometry problem. All right, let's practice again. The decomposition of N2O5 proceeds according to the following equation. So for every 2 N2O5, for every 2 of these, I'm going to make 4 of these and 1 of those. So 4 nitrogen dioxides and 1 oxygen. All right, before we even get to the question, which one's going to go fastest? This is going to be the fastest. Why? Because it's got the largest coefficient. Which one's going to be the slowest? Oxygen. Why? Because it's got the lowest coefficients. What about the dinitrogen pentoxide? It's going to be in the middle. Why? Because its coefficient is in the middle. All right, so it says, if the rate of the decomposition of the dinitrogen pentoxide at a particular instant in the reaction is 4.2 times 10 to the negative 7, what is the rate of the appearance of the the nitrogen dioxide? All right, so let's start with what we know. So we know this, and in the first one they're asking us about this. So what do we know? What's the rate relationship? From this to this one's faster. How much faster? It's twice as fast. So what would the rate of the appearance of nitrogen dioxide be? It would be twice the rate of the disappearance of the dinitrogen pentoxide. So 4.2 times 10 to the negative 7 times 2 would be 8.4 times 10 to the negative 7 molar per second. What about the oxygen? We know the rate of this. What's the rate of this? We know this is a 2 and this is a 1. And what can we say about that relationship? Well, it's going to be slower. How much slower? It's going to be half. So what's it going to be? 2.1 times 10 to the negative 7 molar per second. So if you just use the stoichiometric relationships, you're going to be able to answer these questions really quickly thinking through the problems. So that's instantaneous rate. Hope that was helpful. We got a couple more videos on differential rate, integrated rate, and mechanisms.